So first, I'd like to thank Courtney, who invited me for this talk here. I'm a chemist by training, although in these days I'm really interested in deep learning. And today I'm going to share with you my story about chemical inception. And so this is really about applying inception, which is either a neural network developed by Google or a movie that's 3 layers deep, and how we can use that to make predictions about chemicals. So we've all heard a lot about deep learning today, and I'd like to go through some of the major things that has happened in deep learning. We know about AlphaGo from, I think it's about a year back now, I guess. It has been that long. On how deep learning was critical in developing an AI program that actually mastered one of the most complicated board games known to mankind. Self-driving cars, they're not here yet, but hopefully they'll be there soon. It's also being powered by deep learning algorithms in many ways. And of course, more recently, we might be also seeing real-time translation. So when you look at those sci-fi movies and you're wondering why different aliens can talk to one another, we're going to soon might have a universal translator as well. So besides this, there has also been a couple of controversies with deep learning. As one of the speakers pointed out previously, there was the infamous Microsoft chatbot. But I think part of it is also because of the internet trolls who are actually training the model there. And if you take out your phone, you can ask Siri, what is deep learning, if that's something that you're still trying to figure out. But today I'm going to do Siri's work for you. I'm going to go a very high-level overview of what deep learning is. So hopefully everyone here is familiar with a simple logistic regression. Now, you can think of it as a processing unit where you put in some features, input features, you transform it nonlinearly, and then you feed it some output out. And now imagine if you can arrange these logistic function processing units in a hierarchical fashion and a layered fashion as such. What you have basically is really the foundation underpinnings of a deep neural network. And at a high level, this is all what deep learning is. But why are we interested in deep learning today as opposed to, let's say, a couple years back or a couple decades back when it was first invented? Well, data is number one. There's lots more data than compared to the past. And we've also seen a couple of very good algorithms like dropout and relose that have been merged in the last decade that makes it very easy to train deep neural networks, as well as GPU technology has, I think, matured sufficiently that we can probably do it on a more practical timescale. And so the most important thing to me about what makes deep learning different from traditional machine learning is the ability for representation learning. So what this means is that each layer in the neural network forms its own representation or features about the problem it's trying to solve. And so taking an example from our computer vision colleagues, one possible interpretation or visualization of what the neural network learns might be pixel intensity for the first layer, from which it realizes that, hey, you can actually arrange them in a certain way that you can form lines, use them to form parts of the faces, and finally to the entire face. And the most important thing here that I'm trying to communicate is that the neural network developed this during the training process. It's not something that you have to program explicitly. And so also bearing in mind on the computer vision side, because that's where most of the research has been done, about 3 years after the first neural network model was developed, AlexNet, the field basically achieved what I would call human-level accuracy for top 5 error for image classification. And 3 years is a relatively short time for academics, and it's actually a really remarkable observation in deep learning. And so now we're going to switch gears a bit. We're going to talk about chemistry. How can we apply deep learning to help us solve some of chemistry problems today? So I might have to bore you with the history of chemistry, but the most important thing that you need to take home is that feature engineering chemistry has been going on for a while. So the real foundations of chemistry probably stretch back to the 1880s, where we came up with the concept, or chemists back then came up with the concept of the molecule, and that's something that is being taught at high school level to our students these days. And even before the personal computer was invented, mathematicians actually started developing engineers known as molecular descriptors to describe the chemical structures. And in chemistry, we have also been using machine learning models starting from the 60s, which is known as QSAR or QSPR models, which is really just simple linear regression. And this progressed with SVMs, random forests, and in couple last recent years, also deep neural network models. But more importantly, what I would like to emphasize is that the approach that we are taking still uses the features that we have been developing for the past decades. And today, I'm going to talk about how we can use convolutional neural networks to make chemical predictions without really telling the network much about chemistry and just giving a picture. So basically, one of the interesting side questions that came out from this is, how much chemistry do you need to know to actually predict chemistry? And as a spoiler alert, it turns out it's actually not a lot. So of course, I have to acknowledge the works of the other groups. Although we don't have a lot of Kaggle competitions chemistry, we had two major ones in 2012 and 2014. Both of these Kaggle competitions, or Kaggle-like competitions, were won by teams that use deep learning one way or another. But again, all of them using engineered features that's been developed by the research community. And in some sense, the approach that being used in the field is the approach of deep learning as a machine learning tool. So what do I mean by this? So as chemists, and presumably we are supposed to be intelligent people who are being paid to solve really tough problems, we're supposed to use our heads, we're supposed to look at the chemicals, come up with features, but because the features are not really that correlated well to the complex properties we want to predict, we have to run it through some machine learning model. Could be a linear regression, could be SVMs, could be random forests, could also be deep neural networks, as in the last couple of years. But still, the main thing is that we are the gatekeepers of knowledge, and we are using machine learning in that sense as a tool. So yet another fancy regression or fancy classifier algorithm. So what I'm proposing our work is different is basically how we're going to change the order of things. So instead of coming out with the features on our own, we're basically going to say, all right, I have a bunch of chemical images. I'm going to give it to my neural network. It's going to figure something out for me. And then I'm going to see if the results are reasonable. And maybe I'll try to figure out what the neural network's figuring out. Then construct a QSAR, QSPR model from that. So what we're trying to really achieve is come up with something like a Siri for chemists. So perhaps in the future, every researcher would have a neural network research assistant where we would use that neural network as a first cut for the problem. It's like, all right, here's the data. You take a look at it, tell me what you find, and then I'll see if that's reasonable. At least that's the idea that we want to move forward with. And so in setting up the Chemception neural network architecture, one of the challenges, I would say, is that we had to introduce as little chemistry knowledge as possible in our framework. So the way this is done is that a couple of years back, chemists figured out a way to systemically represent molecules in a string representation. We use available open source software to decode that to a picture, and then we map it onto the grid just to make the picture a bit lower resolution and easier to handle in terms of memory requirements before training it in neural networks. And the amount of knowledge that goes into it really is no different from what is being taught at high school level. So that means that if we had 100 high school students who score 8 in chemistry and were 100% accurate in drawing chemical structures, which will always happen when you do that, and if you take the photographs of that and send it through the neural network, that process would be conceptually equivalent to what we are basically doing at the lab, except ours is generated in an automated fashion. So we managed to try our neural networks on 3 major types of properties. One of them is toxicity, and it's a binary classification task. We also tested on activity, which is a proxy of how well a chemical might work as a drug, as well as the solvation properties, which is, you can think of it as how much heat does the chemical give off when it is dissolved in water. And this would be a regression problem with a much smaller amount of data compared to the rest. And in our empirical studies, we actually tested 3 major different types of neural network architectures, AlexNet, ResNet, and GoogleNet. AlexNet, or more specifically, AlexNet type topology, is a, well, I'll say linear topology of convolutional filters stacked one after the other. ResNet is similar in the sense, except you have a residual link, and I'll go into some of the details later. And GoogleNet is interesting because it has a branch topology, which I'll also go into details later. But visually, what you can see here is that you are going from something that's linear to linear with like links between various blocks, as well as a bunch of complicated stuff over here. And based on our preliminary results, when we try to compute the predictions for toxicity, and this is AUC score, so higher is better, we found that as you increase the neural network complexity in the design, the results actually go up. And there was a certain limitation that we experienced with respect to the width or the depth of the network because the size of our data sets is really that small. So what happens eventually is that we decided to settle on an architecture. The final Chemception architecture is based off Google's work of Inception ResNet v2. So now I'm gonna go into some details about the convolutional neural network design, but it's gonna be pretty high level, so to give you an intuitive feel of what actually the neural network might be doing. So the first important thing in our design is the Inception module that's been developed by Google for GoogleNet. So you may think of Inception modules as a neural network that not just look at a certain part of the picture, but is able to look at different zoom in and zoom out dimensions of the picture at the same time. So that's the whole reason for the branching here, because one branch may be looking at like 3 by 3 pixels, and the other one might scale all the way to like 9 by 9 pixels of the original image. And then it's trying to find correlations between the various features it finds at different spatial scales. And then the residual link that's added on to after the Inception module basically allows you to train neural networks to much deeper depth. The way this is being done is that it actually adds an identity function and sums it up to the activations here. So in other words, you're training around the identity instead of training around 0, and in practice, this usually makes it much easier to train deeper neural networks. In fact, I think the longest ResNet implementation is probably like 1,000 layers long, although we would never train it that long because we don't have enough GPU compute resources for that. Okay, so once we finally decided on the high-level architectural details, we then started to do a limited amount of optimization of the architecture. We tried successfully increasing depths of Chemception as well as changing the widths. And empirically for our data, what we found was that a relatively deep of about 45 layers, but relatively skinny neural network where we only had 16 convolutional filters per layer was actually sufficient and provided the best optimal performance. All right, so now that we have the best so-called optimized architectures, we're going to do some benchmark, and we're going to pit the performance of Chemception with these so-called hand-drawn figures, and we're going to compare them to molecular descriptors, which are engineered features, which are being trained by a couple of different machine learning methods, including the classical one like logistic regression, random forest, but also deep MLP. And these results are both actually being provided by Pandey and co-workers, which is a research group at Stanford, and we are providing the research for Chemception. Okay, so the first one that we take a look is the HIV activity results. As you can see, ours are doing fairly well, I would say, relatively speaking, considering that we don't really tell it anything besides here is a picture of the molecule. And the other machine learning methods actually use engineered features that builds on decades of chemistry research. We're actually performing, I would say, slightly better than the traditional machine learning as well as deep learning algorithms. Moving on to the toxicity data set, this was slightly more challenging because the toxicity data set is actually comprises of 12 different tasks, and it has much less data than the HIV activity data set. Just looking at the performance here, the first two represents your traditional ML algorithms. I believe this is logistic regression and random forest. We're doing better than it, but not necessarily compared to deep neural networks MLP that uses engineered features. I'm going to come back to this later on how to improve Chemception's performance. And lastly, moving on here, we have the predictions from the solvation results. And here, the errors are messy, so lower is better. And compared to the MLP deep learning implementations, we are doing actually better. And this bar chart over here actually represents the result from physics-based models. So physics-based models are basically simulation methods that has been around for decades. And they are the gold standard in the community as to computing this type of physical properties. And we're getting quite close in terms of the validation error. But in terms of the out-of-sample error, it's a bit higher. And again, we'll come back to that on how we can improve Chemception performance. So Chemception is doing pretty okay, but I think it could be doing better as well. And if one thing that's pretty obvious from the data set, which we have, which is extremely limited, is getting a large number of high-quality labeled data is very expensive in chemistry because we have to hire people, we have to pay them money, we have to buy really expensive research equipment. And so data is one of the problems that we have. So one of the ideas that we had was that, and here's where we have to cheat a little bit. We have to teach the neural network a bit more chemistry to push it a bit further. And so remember that the chemical images that I've shown you were like black and white and extremely boring, like a grayscale image, which they are. And we know that there's also RGB images where you might encode the colors in the 3 channels. But instead of encoding the channels, we were wondering, all right, why don't we encode some basic chemical information, again, still being taught at maybe the high school undergrad level, that is pretty easy to figure out, pretty easy to compute, and we put that into the channels of the image. Will the neural network be able to use that information as a way to accelerate its learning of chemistry? And so going back to our general framework here, this additional step, basically what it means is that after drawing out the molecule, we then start annotate the various parts of the drawings with additional chemical information. And sticking in line with the 3 or 4 channel standard, we don't add more than 4 channels of data. So it's not as if we add like 100 channels of chemical information in an effort to train a better neural network. And so the results were actually kind of encouraging as well, because we do see a marginal improvement that when trained with these what I call augmented images, the performance in terms of AUC actually went up for the HIV activity classification, to the point that I am reasonably confident to say that it is doing now better, consistently better than any of the machine learning algorithms being trained on engineered features. Now, going back to the toxicity challenge, remember that we had that little problem with against engineered features on the deep MLP type of machine learning model. With the augmented images, we were able to do significantly better, and now our performance is actually better compared to traditional or deep learning methods that uses these engineered features as well. And the similar story can be repeated for the root mean square error, and this RMSE now, so lower is better, on the solvation free energy predictions. And in fact, the results here is so low that as a chemist, I was really surprised when I saw this, because it's like, this result is very, very close to what chemists consider as the gold standard of accuracy, which is less than 1. But from what we have observed so far, augmenting the images actually does help to really improve accuracy for solvation properties. So in short, what I've shown you is that convolutional neural networks can be really interesting, and they are very useful not only for just identifying cat videos, but we could be used in science as well. And one of the things that we have developed in this work is that we have developed a neural network architecture that uses as little chemical information as possible. And by showing that by sticking to this design philosophy, we can still match many, and in some sense, outperform many of the expert-developed models that are based on decades of feature engineering and design. But one of the most important things is that because we try to take as much as possible a domain-agnostic approach in developing this research program, we suspect that this could be a transferable type of framework where we could start using deep learning as really for the machine intelligence as opposed to just another tool, and try to see if we can actually push forward the boundaries of science. And so going back to the original question that I posed, how much chemistry do you need to know to predict chemistry? If you're a neural network, apparently you don't really need to teach you that much chemistry for it to predict really complicated properties. But I don't think many of you are chemists here, so why do you care? So replace chemistry with a property or a phenomenon or anything you're interested to predict. And let's presume for the moment that you may not have that much domain knowledge in it. And ask yourself a similar question. Now, I can't say with extreme certainty that it's going to work, but I suspect that one caveat, and here's the terms and conditions, if you have a systematic way of representing your problem as an image, and that data is something that a human, given infinite resource, time, and concentration, could come up with, then it's entirely feasible that you might want to run it through a ConvNet first to see if you can find any of the underlying relationships in the data itself. And so some examples just off the top of my head that I can think of is that weather modeling. There is a lot of pictures out there on predicting the weather, and I assume they all have a systematic standard way of representing them. So that might be interesting data. As well as traffic data. Might be useful if you're in a logistic company or interested in just modeling traffic. If, for example, well, this was actually a screenshot from Google, and I'm not sure if they actually store the data, but it's interesting to see if it'd be really cool if it could predict traffic. So in that case, I can drive around it and not get stuck in it. All right, so going forward, having shown that this approach of neural network can work for the domain sciences as well, we still have several questions to address. Number one, and this is not really going away anytime soon, is the small labeled data problem. In the sciences, we sometimes we have lots of data, but the problem is that most of the data is not very well labeled, and it's going to be expensive to label them. So we're going to need to develop new methods and techniques to deal with this small labeled data problem. And the other thing is that even though I've focused my work so far on training neural networks with as little chemistry knowledge as possible, one thing that's implicit is that I have to train a new neural network for every single chemical property I want to predict. And that's going to get tiring really fast because there might be dozens of properties that people are interested in predicting, and we really don't want to repeat the same process over and over again. So one of the questions is that we know that chemistry, there's a vast amount of literature knowledge. Is there any way that we can infuse the neural network with chemical knowledge such that we can develop a neural network that comes pre-trained with some chemistry knowledge that could be really adapted to, let's say, 90% of the problems that chemists are looking at right now? And lastly, I think one of the most exciting things about the work that we're trying to do here is to see how we can actually combine this deep learning machine intelligence with human intelligence to start looking at the really difficult problems in science. And the truth is that there are a lot of challenging problems where our best solution right now is really experience or really trial and error and intuition. And if we could replace that with a systematic and rational way of doing stuff, I think that could be a great acceleration in terms of the way that scientific progress is being made. And so this will be to address the inevitable question, will I lose my job to a neural network in the near future? I don't think so, for a couple of reasons. As humans, we are still, I would say, we're more creative, and we have the ability to learn from very small data. Take driving, for example. There was this video on YouTube of NVIDIA and self-driving cars, and I think they show like before and after was like 3,000 miles of driving. Now, you don't need to drive for 3,000 miles to learn how to drive, hopefully, but the neural network does. And so that lies the problem, but also the advantage of neural network is that it is extremely logical, and it has great stamina. It's going to look at the data set with the same level of logic and attention and consistency that a human never can. So I think there'll be great promise in merging the complementary advantages of both man and machine going forward. Okay, so lastly, I'd like to thank my team involved in this deep learning and computational chemistry research program that we've started recently at PNNL, as well as our funding sources from the lab, Department of Energy, as well as supercomputing resources from XSEED, which is a national supercomputing cluster. All right. Any questions? Yes. That's true. The traffic and the, okay, so the question was that traffic prediction and weather prediction is a time series problem. And with the current implementation, it's not suited for it. But I would say that you can probably do something like a recurrent CNN. So you have a, think of it as a video. So a time series of pictures could be interpreted as a video. And so you might use a recurrent CNN or any other techniques that have been used in video predictions.
I was wondering, when you're trying to map molecules to image space like that, once you get past a relatively small size, these things have deeply three-dimensional structure. I mean, how did you work at all with molecules like, I don't know, proteins or polymers that like fold and stuff like that?
Okay, so the question was that the larger molecules can be really big and they have three-dimensional structures, and did we look at that? The question is no. For the purpose of research, we look at smaller molecules, which generally fit within a 80 by 80 pixel, which in chemical terms is 40 by 40 angstrom. So we did not look at any larger systems. But theoretically, we can do it. All we need is extra memory and GPU horsepower for that.
Thank you.
With the question there? Okay, the question was, have we considered training any chemical reactions for this particular project? No, we have not, but I believe there has been work published by other groups that actually take a look at the chemical predictions like A plus B equals C. And I believe they use, I think it's RNN for that particular model. All right, so I guess I'm standing between you and a coffee break. I will not take any more time from you guys. Thank you for listening.